Good morning, Ben Cohn. Today we're going to talk about the properties of integrals. So we already kind of talked about this in a less formal manner when we went over Riemann sums. But now we're going to talk about integrals more formally, specifically the Fundamental Theorem of Calculus. So the Fundamental Theorem of Calculus, without much justification, is C goes to x of f of t dt. This is called the first fundamental theorem of calculus. So oftentimes it's also just called fundamental theorem of calculus. So taking a look at what this is talking about, or just kind of understand what it's saying. So this is the antiderivative. It is the integral of a function, and specifically it's going to involve x. So the capital F means it's an antiderivative. As we've talked about a little bit earlier, an area under the curve. So this is an integrand integral. It basically looks like a long S, and that's not coincidental because it comes from the idea of a summation. This is f of t. It's just a function of t using the variable t. And this is dt, which I'm going to rewrite as delta t. This is infinitesimally small. This is not infinitesimally small. It's a small finite amount. And then it goes from c to x. So this is kind of earlier when we talked about h with derivatives, and h gets smaller and smaller and smaller until it gets to infinitesimally small. Same idea here, where we have a delta t here, which we can call not infinitely small, but actually have some sort of value, and look at this as a summation where we add up a whole bunch of rectangles, similar to Riemann sum. And so if we look at the summation under a graph, or on a graph, we could say that C starts here, X is here, and this will be T, this graph here will be F of T. And so when we're summing all of these together, we're doing something similar to what we did with Riemann sum, where we're making a whole bunch of rectangles here. Whoop. And one more little rectangle. There we go. And each of these rectangles would be size dt, and the size would be f of t, and it would change based on the function f of t, all the way up to x. And what this is saying is that the antiderivative, basically the area under the curve, is the same as a summation of all these little rectangles. And that's what's being said here. That's the fundamental theorem of calculus. A corollary or implication from this is also that the derivative of f of x, the antiderivative of x, equals f of x. And so the idea is if you take the derivative of an antiderivative, then you just get the function back, which we've already I've hinted at before and talked about before, but that is specifically stated in the first fundamental theorem of calculus. So for this to work, then the antiderivative, big F of x, will have to be continuous and differentiable, meaning that it can't have any pointy edges. So you have to be able to draw the curve without picking up your pen, and then there's no pointy edges. Basically meaning that you can find the derivative at any given point. So if you have a pointy edge, then the derivative on the left side of the pointy edge and the derivative on the right side of the pointy edge will be different, which means that you get some ambiguity, which means the derivative doesn't exist. So that's just a couple of caveats, and that's what is implied here. Now there is the second fundamental theorem of calculus. Oh, looks like I'm going to lose the C. That's okay. Ooh, lost. There we go. If we have, instead of f of x, we have f of b minus f of a, then that will equal a to b f of t dt. And, let's see here, get rid of some of these. There we go. The idea with this is, if we have, I'm going to write up C here, A here, and b here, if we look at this, what this is trying to say is f of b, if we look at this from the first definition we had, this would be c to b of f of t dt minus c to a of f of t dt. And this f of t dt from c to b would be the area from c to b, this area right here. Well, this area of from c to a then, nope, more contrast, would be from c to a, which would be right here. And so this is saying that the integral of b, or integral of f at b minus the integral of f at a will then give you the area from a to b. So this area right here. And that's what we're going to use many, many times later on in calculus. That's going to be the idea behind probably 90% of the integrals that you do. So we're going to get, this is all the information that you need for basically the properties of integrals and the fundamental theorem of calculus. And you're basically going to get two types of problems here. So you'll have the problems that deal with first fundamental theorem of calculus, which on an AP exam you might get 1 to 3. So you can think of it as maybe 2 to 5% of all the problems that you'll get will be first fundamental theorem of calculus problems. And the rest will be what we think of as more traditional integration problems. The other kind of problems you'll get, which are, you'll get from time to time, and they'll be kind of worked into other problems, will be problems that ask you about the properties of integrals and integrations. So easier just to go through a couple of examples. So first example would be find dy dx given that y equals 0 to x of sine of t squared dt. And be like, okay, here's your y, here is your equation, and as soon as you see that there's an x here, and then you have a dummy variable, t, a different variable here in the integral, your first thought should be, okay, this is a fundamental theorem of calculus question. And the way I reason these out is, so you have this y is going to be the integral. So this is basically going to be big f of x. And so to find the derivative of it, we want to get back to f of x. So I'm going to write this in terms of, I'm going to write this in terms, I'm going to call this right here f of x. And so this will be big F of x minus big F of 0. And that's using this property right here. So we have from a to b, 0 to x, f of b minus f of a. Okay? And now it says we want to find the derivative of it. So then we'll take the derivative of both of these. So we take the derivative of one thing minus another thing. We just take the derivative of both of them. So we have f of x derivative, little apostrophe to mean a derivative sign. So from here then, we can see that red. This f of 0, that's just going to be a constant. It's going to be a function of a constant that's going to give us a constant. So when you take the derivative of that, which I should have made a little mark right there, that is going to go to 0. Now this is going to be the derivative of f of x, which we talked about earlier, but I already erased it. The derivative of the antiderivative is just f of x. So this is going to be f of x. Now, one thing you have to consider here is the chain rule. So what we're going to have to then do is multiply by the interior of the derivative. Remember the chain rule, it is something that goes along the lines of f of g of x. Sorry, I'm kind of reusing f here. Prime equals f prime of g of x times g prime of x. Well, for this one here, that went way out of line. There we go. Move you over here. Come back to blue. The derivative of x will just be 1. So you can think of it as derivative of x with respect to x, or dx ddx. Either way, this becomes 1, and you're just left with f of x. Now if we took this problem, we changed it slightly, where we had instead of x, we had x cubed, then we would have f of x cubed times the derivative of x cubed, which would be 3x squared, which would then give us sine of x cubed squared times 3x squared, which would give us the final result of sine of x to the 6th times 3x squared. So the answer to this question would be, so if you find dy dx, given that y equals 0 to x cubed sine of t squared dt, you'd be like, okay, how do we find dy dx? You go through, you write out f of x minus f of 0, antiderivatives. You realize that when you take the derivative, the antiderivative at 0 disappears, and then you're left with the derivative of the antiderivative of x, which is just the function of x, but then you have to multiply by the interior derivative of the interior, which in this case is 3x squared. Now, if you wanted to, you could think of what happened, you could think of it the same way with this big f of 0. When you multiply by the derivative of the interior is a constant, derivative of constant is 0, so what you're really finding here is f of 0 times 0, which is why it disappeared. And we ended up with 3x to the 6 times 3x squared. This is kind of like a standalone problem. You'll find a few of them like these. It's good to understand it, but don't go overboard on being super awesome at this, because they're not really that difficult, and you won't see that many of them. Let's take another look at another example real quick, since we're here. Hop, hop, hop. Click, 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 clack, clack, click. Whoop. But this time, we'll say that we're going from blue. So we're going from 0 to x squared, and we'll do 4t minus 7 dt. So you probably noticed last time, all we do is we take x, we plug it in for t, whatever value's up here, x squared, and then we multiply by the derivative. So then we look at this as f of x squared minus f of 0, big F, antiderivative, integral of such. And so then we take the derivative of both sides to find dy dx, which is what we were asked to find in the beginning. We get f of x squared prime minus antiderivative integral of 0 prime, which goes to 0 itself. We then have f of x squared times 2x, which is 4 times x squared minus 7 times 2x, which we can then simplify to 8x cubed minus 14x. And that's how we do this fundamental theorem of calculus question. Not too hard, but if you're not used to seeing it, then it kind of can catch you off guard. So it's worth doing a handful of those and being like, okay, I see where this is going. The other kind of question would use properties of integrals. So I'm just going to kind of go through them as if kind of like a list, and we'll talk about them as we go. So the first one I want to talk about is an integral times a constant. So if you have integral of a, where a is a constant, f of x dx, where we go from, let's say, b to c, then this would be the same as a times b to c of f of x dx. And this kind of sort of makes sense and feels correct when you think of it in terms of these are just rectangles. Think of it as Riemann sums or just rectangles for area under the curve. If you have a function that gives you this curve, which you find the area under, and you multiply that by, let's say, 3, then that makes sense that 3 times the area under the curve will be 3 times the total area under the curve. And so it kind of makes sense that you can pull out this constant. And that's one of the reasons why I like to think of it in terms of Riemann sums or rectangles. The next one, and I know I'm abusing notation here, and I am sorry for that. I should keep everything BC or AB or not mix it up. It's okay. I'm confident you'll get over it. F of x plus g of x dx. And that would be the same as, so if we have, let's say, something kind of like this, and we have f of x like this and g of x like that, that's saying that if we add the two together and then find the area under it, it would be the same as if we took the area under each of them and added those two separate areas under the curve to each other. So we can break this up into 2 parts. Which, again, you think of it just area under the curve, it's like, oh yeah, that seems almost downright reasonable. F of x dx plus a to b g of x dx. And I don't try to memorize these per se. I just look at them and try and get an intuition of, okay, that's true. And then when I come across them in problems, I'm like, okay, this is how I use them. Next one I want to look at would be a to b of f of x dx plus b to c of f of x dx. So looking at this graphically, what this is going towards, hinting at, or implying, is you have your graph like so. This will be A, this will be B, this will be C, and this is saying that the area from A to B plus the area from B to C will be the same as the total area from A to C. I said, yeah, that seems reasonable. So A to C, f of x dx. Not too bad. Okay, we got that one. Let's go for 4. This one's a little bit less intuitive, but we've already seen it before. So I'm going to say that f of x dx equals negative b to a f of x dx. So this is just saying that if you make rectangles going this way, it'll be the opposite if you have rectangles going that way. And the way I like to, negative sign should be up there. The way I like to think of this is you can be like, okay, this is basically just a summation of f of x times delta x. And this negative is just negative 1. And so what you're kind of sort of doing is you're taking this, doing a summation, f of x times negative delta x. And it's like, okay, so if we're doing negative this little delta x here, kind of seems reasonable that to make it backwards. So if you reverse the limits of integration, the a and the b, then it's going to be negative. And you're just going to, you flip the signs to go the opposite direction. Seems kind of reasonable. And the last two that I like to go over, this one, we've already mentioned it before, but I think it bears repeating, that the integral of f prime of x dx will give you the, I'm going to rewrite this differently. I'm going to say that the derivative of antiderivative equals f of x, which we've already talked about before. The derivative and antiderivative are inverses of each other. And then the last one that I want to talk about is integral of f of x dx equals f of x, antiderivative of x, plus c. And the point I want to draw emphasis to here is the plus c part. When we take the integral of a function, we're going to get a constant c. So if I said, for instance, f of x equals x, then antiderivative of x would be 1/2 x squared. And we'll talk about how to find that later in the next lesson. But this could also equal, oh, there we go, could be 1/2 x squared plus 2. F of x could be 1/2 x squared plus 6. And that's why we write this as the full correct answer is 1/2 x squared plus c. And it might feel kind of like, well, okay, I got, it's just a c, we don't have to worry about it. Sometimes you can get away with that, sometimes you can't. So it's good to keep in mind at least what's going on here. So if we look at this then going backwards, so we found our antiderivatives here, and we want to take the derivative with respect to x and go back to f of x. So we took the derivative of 1/2 x squared plus 2, we would get 2 over 2 x to the first plus 0, the derivative of 2, which would just give us back to x. And you could do the same thing here. You'd take the derivative of 6, and that would give you back to 0. So all of these will give you, when you take the derivative, will give you the same answer. And so they're all equally correct antiderivatives, which is why we would write this as 1/2 x squared plus c. So when you take the integral of a function of x dx, you have to include a constant c on there. So now let's work through a couple of problems to kind of see why these are useful and how they will come in handy. So the first problem I'd like to look at would be the graph of a piecewise linear function, f, as shown above. What is the value of the integral from -1 to 9, so -1 to 9, of 3f of x plus 2 dx? So we don't actually really know what the derivative of this is. All we know is what the derivative of f of x dx is. And we know that because it's area under the curve. And, okay, we don't know it yet, but we can figure it out, and we will. So what we want to do is rewrite this problem in terms of this. So first thing we do then is we will say, all right, so since we have an addition sign, we can break it up. So -1 to 9, 3f of x dx plus -1 to 9 of 2 dx. We then pull the 3 out, and we have 3 -1 to 9 f of x dx plus -1 to 9 2 dx. Now we really haven't learned how to do antiderivatives yet, so we don't really know how to do this second part, but we could figure it out. And so it's going to be then, this will be x, this will be f of x, and we'll say, well, let's call this y. There we go, y, and we're going to have 2 here, so this is 2, and we're going to find the area under the curve from -1 to 9. So to find that, we look at this and be like, okay, well, we just find the area under the curve, and this would be 9 minus -1, which is 10, because the -1 becomes +1, because it's double negative. So we have a 10 by 2, which is 20. So we have an area of 20 under this curve. Now the way we'd actually do it, which we'll learn in the next lesson, would be we take the integral of 2, which is 2x, and we evaluate it from 9 to -1, which we evaluate it by doing 2 times 9 minus 2 times -1, which gives us the same answer of 20. Now over here, we have 3 times f of x dx. So the integral of f of x dx is just going to be area under the curve. So this is 1, 2, 3 times -1, which is going to give us -3. That's an area of -3. So these two areas, there's going to be let's see here. What's the easiest way to do this? I'm just going to call this -1/2. Get rid of some of this. This will be -1/2. Change colors just to keep things a little bit clearer. this is 2 by 2. 2 by 2 is 2 times 2 is 4. 4 divided by 2 is 2. So the area of a triangle is 1/2 base times height. That's 2 times 1, 2, 3, 4. 1, 2, 3, 4. 2 times 4 is 8. 8 divided by 2 is 4. So we have 2 times 4, or 2 plus 4, which is 6. 6 minus 3 is 3. 3 minus 1/2 is 2.5. So we have integral from -1 to 9 f of x dx equals 2.5. So we can plug that in here. So we have 3 times 2.5 plus 20, because our 20 is over here, which gives us 27.5. Look over here, and excellent. That's one of the possible answers. To kind of backtrack and look and see what we did here. Oh, nope. Erase some of these. There we go. We had a integral here with the 3, and 3 times f of x, and then plus 2. So the first thing it did is we separated them based on the addition sign. So we had 2 integrals. We could then solve the integral of -1 to 9 of 2, which is just the area under the curve of y equals 2. And then we could factor out the 3, and then find the integral of -1 to 9 of f of x dx. And that gave us 2.5. 2.5 then times 3 became 7. We added that to 20, which is the area under the curve for y equals 2. And we got a total answer of 27.5. And that's one of the ways we can use the properties of integrals to find a solution. Looking at another problem, the graph of f prime, the derivative function of f, consists of 2 line segments and a semicircle, as shown in the figure above. If f of 2 equals 1, then f of -5 equals such and such. Okay, so we're given f prime, and we want to find the find it in terms of f, the function f. So to convert f prime to the function f, we're going to have to do the integral. The integral of the derivative will just be the function, so we'll find the area under the curve. So we're given f of -5, and we're given f of 2. So really don't know where to start from here, but I'm going to use the data that I'm given. So I'm going to say, so we take the integral from -5 to 2 of f prime of x dx, and that'll equal f of 2 minus f of -5. Now we're normally used to using antiderivatives here, the big F's, and the normal function right here. But since they gave us f prime of x, we're now using f prime of x here and the antiderivative or integral of f prime of x, which is just the function here. So I just wrote up the information that we were given. And they gave us right here that f of 2 equals 1. And they're trying to find this value right here. So to do that then, we know we can find this one right here. This is the area under the curve. We're given this one, and we can rearrange things to find f of -5. So I'm going to rearrange it first and then solve. So moving it to the other side, we have f of 2 minus integral -5 to 2 of f prime of x dx. Now I kind of made that easy. I'm like, oh, this is where I went. It's not easy. And I understand. It's one of those things where with these sort of AP problems, it feels like 2/3 of the problem is just kind of understanding what they're trying to ask. Once you get everything set up, you're like, oh, okay, this is where I go. But understanding the question is probably 2/3 of most of these problems. And so even though I kind of made it easy by being like, well, this is what we do, I understand that it's not as easy as I pretend to make it out to be. Okay, so now we need to find the area from -5 to 2. So it'll be from here to there. So this is 2, 1, 2, 3. 2 times 3 is 6. 6 divided by 2 is 3. The area under a triangle is 1/2 base times height. Now we want to find the area of this triangle. Area equals pi r squared for a circle, which will be 4 because it's radius of 2. 4 pi, but since we have area, we only have half circle, that's going to be 2 pi. So our total area, I call this area total, will be positive 3 minus 2 pi. So we have this equals 1 minus quantity 3 minus 2 pi. Distribute the negative, and we are left with 2 pi minus 2 as the answer. Hup, hup. That's even a possible answer, which is nice. And so the answer for this one would then be A. So to back up, see what we did here. We were given a graph, f prime of x, and we were told that we're given some information about the function f of 2 and f of negative 5. We really didn't know what to do, and so we just kind of used our definition of second fundamental theorem of calculus using an integral. So we use integral from negative 5 to 2 because those are the only points that were given to us. Maybe it would work out. We wrote things out. We figured out that we had an equation with only one unknown. And when you have one equation, one unknown, you can solve for that one unknown, which we did. We got 2 pi minus 2 using the area under the curve. So that is how you approach this problem. A little bit, most of this problem is understanding what they're asking, and then very little is actually just kind of working through the process. All right, let's try one more. The graph of a differential function, f, as shown above, is shown above. If h of x equals 0 to x f of t dt, okay, this is a hint here that we have a fundamental theorem of calculus issue, okay? Which of the following is true? Okay, so we know from the fundamental theorem of calculus that this will be f of x. And they're looking at point 6 here, at x equals 6. And we know that, okay. Okay, so this is f of x, because that's the definition of fundamental theorem of calculus right here. This is big F of x, antiderivative, which is the area under the curve. The area under the curve from 0 to 6, even if it's not drawn to scale, we know there's an intercept point right there. That's negative, and so the area under the curve, or the integral antiderivative of x for this f of 6, for x equals 6, f of 6, will be less than 0, because that's the area under the curve. That's definition of the fundamental theorem of calculus. So we know f of 6 is less than 0. This is the graph of f of x, and we know that f of x at point 6 equals 0 because it crosses it. And then, so this is h of x. And so the derivative of the antiderivative will be the normal function. So this would be h prime of x, which would be f of x, which would equal 0 because we know it's a root. And then if we look here at the slope, we can see that it's an upward slope. And so f prime of x, which would correlate to h double prime of x, would be greater than 0 because it's an upward slope. And so we have a relation here. We know 1 is less than 0, 1 equals 0, and 1 is greater than 0. So we look over here at this one right here. So we have h of 6. I know these are all x, but I should be writing 6 here. So 6, 6. No, not going to do that. That's just bad omen. So we have h of x at 6. We have, this is less than 0, which is less than 0, which is less than something that's greater than 0. So right here, A is going to be true. And this is a challenging problem, not because they really do anything abstractly difficult, but because it's hard to understand what's being said here. And so the key to start this off is you see this, you say, all right, graph of a differentiable function, f is shown above. So we have graph of f, and they have to say differentiable so that you can know you can take the derivative of it. And you have to be like, okay, this is fundamental theorem of calculus. This is big F of x. Big F of x equals that, and then you have to know that it correlates to area under the curve. From there, then, you have to be able to look at this and be like, okay, that big F of x relates to f of x through the derivative. And here we know that the graph of f gives us 0 at f of 6, or h prime of 6. They're both the same thing. And then we take the derivative one more time. We look at the slope, and we're like, okay, it's a positive slope. It goes up. And that f prime of x that we just kind of decided to make this new variable, no, we didn't just make it. It's given us right here. We're good. It's fine. That relates to h double prime of x. So this question, not hard, but it is a little bit confusing. And that's a real challenge here. But once you kind of see where they're going with that and how things relate, then it's like, okay, this is what the answer is. This is what the problem's really asking. So I hope that helped with getting a kind of idea for the very basis of fundamental theorem of calculus and some of the properties that you see with integrals. Now we're actually going to spend the vast majority of the rest of the classes here going over how to find integrals, how to take a function f of x and turn it into an integral. And that'll be probably about half the AP exam, because they get challenging. It is really a hill to climb, a mountain to scale, so to speak. Appreciate you coming. I will see you next time. Thank you much.